everyone, my name is Divya. I am a postdoctoral fellow in the AstroSat Science Support Cell at AICA. Today I will be presenting our work, research work, in which we have studied the comptonizing medium of black hole X-ray binary source, MAXI J1535, through type C quasi-periodic oscillations. And in this work, here's the list of my collaborators who have contributed. This is the light curve and the hardness intensity plot I'm showing. We have plotted using the NISR XTA observation of September to October 2017. So on the left panel is it's the light curve, and on the right panel it's the hardness intensity plot. Here I'm showing only those data points for which we have found the type C QPO was present. So initially we have noticed that in the light curve the intensity first drops, and that then it keeps on increasing. So these color bars represent the QPO frequency from 2 to 9. So red goes from 2, and then blue is the 9 hertz. The QPO frequency we have observed that also increasing with the intensity and taking its maxima when the intensity is maximum at around 9 hertz. Then it drops as the source makes a transition to a soft intermediate state to around 4 to 5 hertz. In the hardness intensity plot, one can see the evolution of the source and the state transition from hard to soft state. That's the hardness ratio, which is the ratio of photons in the 5 to 10 keV band divided by the ratio of photons in 0.5 to 2 keV band. It first decreases for initial days, and then it keeps on, it first increases, then it keeps on decreasing with an increased QPO frequency. As the source goes to this soft intermediate state, again the QPO frequency drops to around 4 to 5 hertz. Next, we extract the power density spectra for the source, and we found that there is a presence of type C QPO with varying frequency of 1.8 to 5 hertz. This is the PDS I'm showing here, and these are the QPO, the Lorentzians, and the harmonic component one can see. In addition, we have found that as the QPO frequency increases above a particular frequency at around 4 to 5 hertz, we see an additional subharmonic component at around 4.5 hertz. This one I'm showing here. Next, we extract the spectra and fit the spectra with this model EBABS, which takes care of the interstellar absorption, the DISPV, which takes care of the non-thermal emission, NTH-COM, which takes care of the comptonizing medium, the non-thermal one, then the Gaussian, which takes care of the iron line if it's required. For some data point, it was not required. Then I'm showing here the plot, the evolution of the spectral parameters, the gamma and the KTN with time. So here also the gamma and the KTN first drops, like the intensity was dropping for initial days, and then the gamma goes to around 2.6, and then it's much more scattered, so it's hard to say what it is. Then in KTN, it replicates the light curve if one notice carefully. Next, we extract the RMS and the lag spectra and fit it at the QPO frequency and fit it with comptonization model proposed by Carpozas et al. 2021, which was originally developed for high frequency QPOs in neutron stars by Kumar and Misra et al. So this model assumes that there is a disk and a spherical corona. So it assumes the corona is symmetric, and let's say it has a length or the width of L. Then soft photons from the disk are injecting this corona, and then some of the fraction photons are getting reflected, that we say the feedback fraction. And so there are two assumptions we are making here. First, the corona is symmetric, and second, the coronal density is uniform. So the next question is why we are fitting the RMS and the lag spectra with this model, which was originally proposed for neutron stars. So the rationale behind our application of this model to type C QPOs and DHX-RBs is that the RMS of these QPOs can be as high as 15% at around 200 kV, as reported by Ma et al. 2021. And at those energies, comptonization dominates. So it has to be the only mechanism which is responsible for the observed RMS and the lag spectra. And here are the plots. So first, it's the fractional RMS spectra and the lag spectra at the 3 QPO frequency I'm showing. It's the fitted one. So together with the spectral parameters, we fit the spectra, we get the parameters, and together with those parameters, we fit the RMS and the lag spectra with the comptonization model. So here for plotting the phase lag spectra, we are keeping this reference energy band as 8 to 12 kV. So the lag is soft here. Next, we have noticed that the spectral parameters and the comptonization model parameters, they all are behaving in a different fashion above or below a particular QPO frequency. So what we did here, we plotted these parameters as a function of QPO frequency. And so clearly one can see the slope is changing as the QPO frequency increases. So we assume that this is because of something intrinsic. This is because of something intrinsic to the source, and we assume here that it is happening for all the parameters at a same frequency, and we fit these parameters with a broken line. And obviously we did this chi-statistics, and we found that it reduces. So here I'm showing this plot of gamma as a function of QPO frequency fitted with a broken line. The blue one is a broken line and the red one is a linear. Yeah. So here also KTN, the same. The red one is a linear and the blue one is the broken line. This is just to show that broken power line fits the data better. And this shaded area, so what we did, we tied this QPO frequency, which we assume that it is intrinsic to the source. So all the parameters show this behavior at this single frequency only. So we tied this frequency and fitted all these plots with either the broken power line or the broken power law. So we call this frequency the critical frequency. So here I'm showing the comptonization model fitted parameters, the KTS, the temperature of the disk, the multi-temperature disk. And again, the blue one is the broken power law, and the red one is the power law only. And the L is the size of the corona. So size is decreasing from 10 to raise the power 4 to 10 to raise the power 3 kilometer. It's in kilometer as a function of QPO frequency. So we fitted it and we got the estimate of this critical frequency is 3.2 hertz. And this shaded area represents the 3 sigma confidence interval. This is eta, the feedback fraction, though it was not showing any pattern, but we still included it while fitting, while getting the estimate of the of this critical frequency. And time lags, when we plotted this 2-band time lag, we have noticed that it's also following that pattern. So we included these plots. So even if we exclude the feedback fraction, the eta, the critical frequency is same, we have noticed. Then the next question is why it is happening, why these parameters, all the spectral parameters or the comptonization and the lags are behaving differently above and below this frequency. So we did some literature survey and we found that there is a paper by Russell et al. In which they have found radio jet quenching in the same period where we are seeing this this break frequency or the critical frequency. So this is the shaded area where Russell et al. Has reported a radio jet quenching period. So if you see carefully, this is at around 3.2 hertz. I mean, after 3.2 hertz, the QPO appears. This radio jet quenching starts. So we found that the critical frequency appears in the same period when emission of the radio jet quenches for this source. So that is the relevance of this particular frequency here. So yes, we analyzed the NISR observation of MAXI J1535 during its initial phase of outburst in September and October 2017. The lag spectra of the type C QPO, the spectral parameters, the model fitted comptonization parameters, they all change in a similar manner as the QPO frequency increases from 1.8 hertz to 9 hertz. And we show that these quantities show a significant break in relation at QPO frequency around 3.2 hertz. And we also found that the corona is shrinking from 10 to raise the power 4 to 10 to raise the power 3 kilometer as a source goes from a hard to softer state or soft intermediate state. We have noticed a high feedback fraction value we are getting here, so which indicates that during this whole period of contraction, the corona covers a large portion of the accretion disk, which is consistent with the value what we are getting for the coronal size. And here is my summary. So we found that the comptonizing medium of MAXI J1535 through varying type C QPO frequency ranging from 1.8 to 9 hertz could be explained as a corona of shrinking size from 10 to the power 4 kilometer to 10 to the power 3 kilometer. And yes, we have reported for the first time this critical frequency, which is 3.2 hertz for this source. And interestingly, this critical frequency appears in the same period when the radio jet quenches for this source. And if you remember, I have shown you that we have observed an additional subharmonic component at 1.5 hertz in our PDS above a particular frequency. So we speculate that we see the break frequency is the same frequency above which we were seeing this additional component for the source. And that's it. Thank you.
Thank you, Divya. Are there any questions? Are there any online questions?
Yeah, here is a question.
Hello, Yash Bhargav.
Yeah.
So what is the, like, if you convert from kilometers to RG, what is
Yeah,
the
so as I told, the mass measurements with the optical observation is not available. But if you assume it's a 10 solar mass black hole, it's large. It's around 67 RG for 10 to the power 3 kilometer.
No questions online also. Okay, thank you, Divya.
Okay.
But just wanted to know.
Yeah.
When you started with saying that when you say the corona size is 10 to the power 3 to 10 to the power 4.
Yeah.
What exactly do you mean? Just the radius thing, or how are you saying N?
Yeah, it's the width. It's the characteristic length. It's the width of the corona.
Thanks.
Okay. Thank you.
Ranjeev?
Yes, I'm ready.
I request you to go ahead.
Okay, let me start. I'll repeat the same question which everybody says online. Can you see my slides and can you hear me? Hello?
We can hear you here.
Yes.
Can you see my slides?
Yes.
Okay, thanks. I'll start then without. Should I start now, Seetha?
Yes, please.
Yeah. I would like to thank the organizers for asking me to give this talk, and I'm sorry that I could not do this in person. It's very unfortunate. I don't like online talks, but this can't be helped. I'll start with a tribute to T. Padmanabhan, Paddy as we know him, and the reason is that it is Paddy who explained to me the connection between puzzles which we do and the research that we do in our naval life, and that is the theme of my talk today. So hence I thought I'll just give a tribute to him. And I think my title needs some explanation, that what do I mean by puzzle challenges? So let me go a little abstract here to explain what I mean here. Suppose we ask questions in astrophysics, and many of these questions remain unanswered. So we can ask, what is the broad reasons why a question in astrophysics in general is unanswered? And a couple of obvious reasons for that. The first obvious reason is insufficient data. We need much more high resolution data, longer data, and that's the reason why we build all these telescopes, larger telescopes, and we keep going ahead and doing, because we believe that insufficient data is one of the prime reasons why we cannot answer questions in astrophysics. There is one more reason, which is also very generic, and that is that we don't sometimes understand the underlying physics. This could vary between the fact that we don't know what dark matter, dark energy is in cosmology, to the more ideal thing that we don't know nonlinearity physics. In particular, we don't know turbulence. we don't understand the quantitative nature of turbulence. So that is why uh, we sometimes cannot answer fundamental questions in astrophysics despite having sufficient data. Often the problems are both of this. We don't understand the underlying physics and we don't have sufficient data. So this is the kind of generic one. And this is what most people talk about. However, there's one more category of questions which we cannot answer. And that is the category which I'm going to talk about right now. And that is when it's neither of the above. It seems as if we have all the data we want. It seems also that we understand the underlying physics okay, or reasonably well. I mean, at least for the context of the question. And then still, we are unable to answer that question. I would classify such a situation as a puzzle, because puzzles are where you have all the information, but you still have to find out what the solution is. And they pose a challenge because we want to find a solution to these things, and we don't have an excuse that there is no sufficient data and that the underlying physics is not allowed. And however, this is sometimes subjective as we'll go along. And this because the subjectiveness comes in what is a reasonable solution. You can always come up with a weird solution, but you need to come up with a reasonable solution. So that is what I meant by puzzle challenges, and I will be emphasizing on the puzzle challenges from AstroSat observation of only X-ray binaries, while these things exist for all fields everywhere. So before I proceed, I would like to list out my collaborators. I have a lot of list of collaborators who work with me on X-ray binaries using AstroSat data in particular. And many of the students and postdocs are very aggressive and fairly dangerous. So I thought I'll just list out their names and go along, although I will not be able to cover all these people's work at there. Now, all these people think that they're working on X-ray binaries, which they think is this, that you have a central object, which is a kind of a black hole or neutron star, a star going around, and the star is close to thing, and it forms an accretion disk. And this accretion disk is the one which heats up, and by this heating up, it gives you radiation, X-rays, and emission. This is what we see, and this is all. And this is the kind of beautiful picture they have in mind. But in reality, what we really know is this, that what we know is that there is something like what we call a standard cold accretion disk. It is there, we mostly believe it. Then there is some strange thing which we call a hot disk, corona, hot inner flow. And what we believe in generic is that low energy photons from the cold disk get comptonized on this hot disk corona and produce high energy X-ray photons. So even the geometry of this is not very well constrained, and there are doubts, but this is the broad geometry that most people follow. And this kind of a scenario is the only thing we know concretely. So let me just make sure you understand this. There's a cold disk which forms a kind of a low energy component here, and there's a hot disk which forms a high energy component, which is due to comptonization of these photons. And the relative strength between them gives you variations in the spectral states, which I will not go into. And the essential part from what we have understood so far is that, I'll repeat, that X-ray binaries have standard accretion disk which emit low energy photons, and then they have something called a hot corona, hot disk, hot inner flow. All are different names given the same thing, which produce high energy greater than 10 keV photons through thermal compilation. This is the as much background I think we can start with. But since dealing with AstroSat lax PC, the primary motivation here is timing. These sources are highly variable, like this is the Cygnus X1 light curve. These are not error bars, these are the actual variations of the source. And since it's difficult to understand this kind of a light curve directly or variation, what we do is we do a Fourier transform of this light curve, take the square, and which gives us something called a power spectrum. The power spectrum tells us how the source is varying at different frequencies. And for example, in Cygnus X1, in different times, it shows different kind of power spectrums. It all shows broad noise variations and noises and all that. This was all known before. What AstroSat could do was it could actually, let me go back here for a moment. It actually could measure the fractional RMS at different frequencies. as a function of energy. So let's say at 1 hertz, that is around 1 second time scale, we can say that how the fractional RMS changes with energy, and that's called a fractional RMS energy. And also we could measure a time lag at that frequency. That means how these high energy photons lag behind or come before the low energy ones. Using this information and using this kind of a spectral modeling, we can now actually, using AstroSat data, we can now actually say what is varying in the disk, and subsequently or beforehand, what is varying in this hot disk. So this is quite complicated, but we have been now able to identify this from such kind of thing, and there are lots of papers doing that. So the bottom line here is, after doing all this work, sometimes you get a very simple result, and the simple result we get is, if you see high energy photons varying later, it means that whatever variability you're looking at, it originated in the cold disk and then moved to the hot one, right? That makes sense. In other hand, if you see the low energy photons very later, then it means that the soft energy photons, then the variability originated in the hot corona and then moved to the cold disk. So that's kind of an obvious kind of a relationship which we can get from the time lags. However, the real interesting point is something called quasi-periodic oscillations. This we see in many black hole systems. Here's an example of one in J15. You see a 3 hertz. There's something very oscillating in something which oscillates coherently in this systems. And there's a lot of debate on what they are. There could be lens steering precision of the hot disk, which means that this hot disk wobbles due to general electric effects and due to something called lens steering precision. And because of wobbling, we see this oscillation. It could be just as that this hot disk is oscillating as an instability, and it's just oscillating means it's just squeezing up and down. And this kind of oscillation could also occur in the time scales of sound crossing times. And all these time scales are modified by generativity. And for example, we have used AstroSat data to find out how does the radius of this inferred radius of this hot disk vary with this QPO frequency, and we have seen that it can vary. Our data seems to suggest that it is due to the that it matches with the generalistic time scale of the time it takes for sound to cross the system. And it has been this kind of idea has also been confirmed by HMXT, which is a different satellite launched by the Chinese out there. But this is not the part of it. All this, what it means in this kind of thing is that it comes to the first category of problem, that we have insufficient understanding of the underlying physics, and therefore we have to struggle through all this kind of a situation and rely on data, and our data is also insufficient, and therefore we don't understand these questions very well. But let's look at the time lags. Now in time lags, again for the quasi-periodic oscillation, we can make a generic statement that if the high energy photons vary later, that means the QPO originates in the cold disk. If it is the low energy photons very later, then the QPO originates in the hot disk. This seems fairly model independent and fairly concrete, so we can go ahead with that. And indeed, if you look at another black hole transit, I could have shown you several ones, like this J161524. And now this is the black line where you see the time lag. Then the coming down part means that the low energy photons are coming later. The high energy photons come first, the low energy photons come later, which means that for this quasi-periodic oscillation, the quasi-periodic oscillation originates in the hot disk, which makes sense. That's what both these models talk about, that this is in the software. However, we have coming to the first puzzle, which I have in my, is you also have something like, in this case, a subharmonic. This frequency of this variation is half of that, so it should be related to this. But this subharmonic has again a soft lag, which means that the sign is correct, but the value is different. To show you some, but they're more important ones. For GR915, for example, for a perfect QPO at 3.5, there is a perfect harmonic at twice the frequency, 7 hertz. The time lag for the main QPO is soft, while the time lag for the high frequency, for the harmonic, is hard. So it seems as if you're going to say that the QPO originates in the hot disk, propagates to the cold one, while this harmonic is exactly the opposite. It seems to originate in the cold disk and go to the hot. This is my first puzzle number one. We don't know the answer to this question. And the frustrating thing here is this doesn't seem to rely on any underlying physics, as I was mentioning, or lack of data. We've got very good data. So what could be its origin? Well, for this puzzle, let me give you some ideas which we have done. And the generic idea is to push it to a level where you say, we don't know the underlying physics. And the statement here are harmonics are produced by nonlinear processes, complicated. There are possible explanations because nonlinearity is something which we get scared about. We don't know very well, and we have worked on something of that. So this could be a complicated process and hence may not classify exactly as a perfect puzzle. There are also that harmonics could be caused by non-axisymmetric patterns in a precessing disk, right? Suppose you have a disk which is precessing, wobbling, you will see a main QPO because of the wobbling frequency. You may say harmonic if there are spots in this wobbling disk, and the spots may cause it to oscillate. So you see them twice a cycle. And this wobbling can be non-axisymmetric. Again, it's a complicated thing. And there people have been talking about this, that we cannot really rely that on these lags, what we can do, unless we have a very good model. But let me tell you that this is extremely frustrating. We should have a good model of doing this, but we don't have one for them. That's a puzzle number one. But you can perhaps say that we can get away with this in some region. Let me show you one more. I'll show you three puzzles. This now I'll show you the second one, which is I think fairly more dramatic. This is the same source. I think I mean no, it's a different. The black hole source MAXI J1535 571, and this has been shown by AstroSat that the QPO frequency perfectly correlates with Palo gamma, something like what Divya was showing you before, but this is a much better correlation shown by Yash Bhargav. And so this shows that there's a QPO phenomena where at different times the frequency of the QPO changes and is highly correlated to the Palo gamma, which comes out here. Right. This is the problem here is that we have been working on the time lags from this source of QPO frequencies. And this is the time lag between the hard energy and the low energy forms. And we find a phenomenal thing that at high frequencies, you see, this frequency goes from 1.7 to 2.8 hertz. At higher frequencies, from 2 to 2.8, the time lags are negative, which means that these frequencies originate in the corona and go to the disk. But at the lower frequency, at frequencies lower than 2 hertz, it changes sign. They are now becoming positive, which means that for QPOs lower than 2 hertz, the origin seems to be the disk and going into the corona. How can this ever happen in this whole thing? How can the origin of that at one moment the origin of QPO changes from a disk to a thing and goes up? So that's a very strange result. And let me counter that. These results, I'm going to show you only AstroSat data, but it is not that these have only been seen by AstroSat. They were previously seen by the earlier timing instrument called RXT, but this time lags was not very well done in RXT because of its limited energy bands. So people had doubts on it. But I mean, some people had some doubts on whether it could be done correctly, but with lag species high energy band, we are sure. So this kind of phenomena, we are now completely sure that it's happening, that the time lag are changing signs as the QPO frequency changes. So it's the same phenomena. And why do we think the same phenomena? Because the frequency, look at the slight correlation between the index and all. It doesn't seem that there is a different, it's a different phenomena below 2 hertz and within 2 hertz, but the time lag changes. What could be the possible explanations? Well, there is really no idea. It is a puzzle. That is why I'm putting it forward. It could be complex geometric effects of a precessing corona. There are papers written on this, but it is not very clear what do they mean and why should it be that complex in a way. There's also another interesting idea we're looking at is that there are both way feedback signals between a corona and a disk, but how does it work and where is the origin of the QPO anyway, even if there is a both way feedback systems, and we are working on that to see if we can look at this kind of a puzzle out there. So this was my second puzzle, and let me go on to the final one. And this is a paper which is not yet published. In fact, the results are not yet out. The previous speaker, Divya, would be submitting this in the future. I mean, yeah, I mean in the distant, I mean not so distant future. But let me show you this. But this is not preliminary result. We have worked through this very carefully, and we know that this is correct. So this is not preliminary result, but has not been submitted yet. This is another QPO of the source J1535, which is a black hole system from AstroSat XPC. The black, red, green, blue points shows the power spectrum in different energy bands. The black is the low one, then you go to slightly higher, green is slightly higher, and the blue is highest. You see these features out here, which is a QPO, which we can look at very carefully. But even from the eye, you can, and from this case, you can clearly see that the QPO frequency changes with energy. Let me repeat that. The QPO frequency changes with energy. And this is what we get if you plot it out, that this is the energy in kV, the QPO frequency is changing. Okay. Now, this is really, really bad. Really, really bad means really, really challenging. How are you going to get the QPO frequency change with energy? Let me get back to this model to explain what I mean. The different energy photons are coming from different parts, which is not generically true. You see, what happens is this is comptonization. You have one photon coming in, it scatters all over a place, and then comes out and becomes high energy one. So if I look at a high energy photon, I cannot say it came from this part or that part. It started from the cold disk, went all over the place, scattered, and came back. So within the hot disk, there should not be any differentiation between where the photon has come from. So the fact that the QPO frequency is different is a bewildering thing in this kind of a situation. Okay, even if you discard that, you say, no, there's some method by which the high energy photons are coming from this part, the inner part, the low energy photons are coming from this part, this part, and then the lowest energy is coming from here. Somehow the frequency is changing from here to there by a huge amount, by 1 Hertz. When the frequency changes, something like they will become incoherent, and we are observing this for thousands of seconds. And then we measure this. In thousands of seconds, the phase between this and this QPO would completely be gone, and they'll be completely unconnected. Meanwhile, in that 1,000 seconds, matter has flown from here to there many times. I mean, the whole thing has been swept aside, and matter has been, whatever was here has all the way gone there. Yet, we see this variation in QPO frequency. And I will make a confession here as a anecdote for the younger people to learn from my mistakes. This is not the first time we are seeing a QPO frequency change with energy. About 7 years ago, a paper reported this by using RXT results. I completely dismissed that paper. I thought that either the analysis was wrong or the data was wrong. But I didn't worry about it too much. And anyway, at that time, just 6 years down the line, we were getting very busy with AstroSat. And I started working on AstroSat XPC data, but not worrying about that paper which said that there was a frequency shift with energy. Because I thought that is impossible. And even when we were looking at about 5-6 years ago, when we were trying to publish the first results of AstroSat, one of the students actually showed me that there was a shift in the frequency. And then I verified again, and I thought that I saw a shift. At that time, Professor Yadav and we were trying to submit this first papers on AstroSat results. What we did that time was we kept this aside. We said, this is too controversial. Let's not worry about it. Let us first get our basic wonderful results, which we already had from AstroSat out, and we published that, and leaving the results out. And I conveniently forgot about it. Why did I forget about it? Because the results are so bad. I mean, so bad means they're so against my understanding of the system that the mind blocks it out. I forgot about it. But last year, I see a paper by this Chinese HMXC satellite where they claim the same thing. they have different instruments on board, so they cannot be very reliable. But they see that the QPO frequency changes with energy, and that's why when I got back and I saw this, verified it, and we have seen this for now 3-4 observations that indeed the QPO frequency is changing with energy. This is so difficult that I had to look at an alternate idea, and the alternate idea is kind of a contract one, that instead of one, you have two QPO frequencies, one at 5.8 hertz, one at 6.7 hertz, for example. They don't vary, but they're two QPO frequencies, and the relative strength of these two QPO frequencies changes with energy. Something like this, that the QPO frequency at 6.7 hertz is low and then keeps increasing, and at high energy it becomes dominant, and the QPO frequency of 5.8 is high, but this is unsatisfactory, unreasonable, but it's still a possible solution. First of all, why do you have two QPO frequencies? And then you have to fine tune these things so that the low energy one goes down, the high energy one goes up. It looks unsatisfactory, but this is what we have. And there's nothing about underlying physics, nothing about things, and we have nothing about wrong with the data. So we have a puzzle in hand in the whole thing. So I know we're running out, so I will more quickly finish here. But like I said, in this kind of my talk on there, I don't have conclusions. I only have questions. Since I have the questions, I would expect answers. And I know there is a time constraint, and some of you may not be able to give me the answers right now. But I would appreciate if you send me the answers over email, and especially in tech format, either in AppJ or MNS format. And but please leave the authorship column out. I will fill that myself. But I'm waiting for your answers here. So thank you very much.
Okay, Ranjeev. Are there any questions from here?
Answers, Seetha.
No, but we can ask some more questions, some more puzzles to the basket.
Yes.
Yeah.
Those will come later, na, as you said.
So anybody here? Is there anyone there? Online? Ranjeev, is this, I know you are probably the best person to answer this. Do you think when we are comparing this, especially with GRS, the source is so variable, both in time and in spectral states. Do you think when we are comparing QPOs like this, its evolution, the time element is lost there? How long it took to reach 9 hertz, etc. So, do you think that also has to be brought in? That is one question. Second is there something like, I mean, this is very naive, something like a mode coupling between these two frequencies?
So I couldn't get the last question, please.
Is this like in the regular frequencies you have mode couplings?
Mm-hmm. Yes.
So could this be something like that?
Yes. Yeah. I'll answer. Yes. Actually, the time varying nature of these frequencies are very important. And luckily, we cannot hide behind the fact that we don't have data for that. Because what we can do is, like species with all three proportional contours on, we can do something called a dynamical power spectrum, where we look at how the QPO frequency evolves with time. Let me answer your question first. First part is that when we are looking at these QPO frequencies, let's say at 2000, 3000 seconds, the average flux is steady. So that is not a problem. The second is we can look at every 200, 300 seconds to see where the QPO frequency is changing with energy, changing or not. We do see changes, but sometimes, but we can measure this. We can actually quantify this changes because of the high effective area of like species, especially when we had all three instruments on board. So that doesn't seem to be the issue here. That the second question is, of course, you can always have two frequencies close by, mode coupling and all, but that begs the question again of what is the reason for this, and why does it have such a deceiving energy dependence, which makes us think that it is the QPO frequency changing with energy.
Okay. Anything else? No? Okay, thanks, Ranjeev.
Thank you.
Some of your our younger colleagues will give you answers in text format.
Sure. Thanks. Thanks.
Thank you.
I'm waiting for it.
Wonderful.
Tomorrow, Tuesday, 4 p.m. is the deadline, please. Yeah. Okay.
Okay.
Bye.
Thanks. Okay, so now let's go on to Pinaki Roy. Can you unshare your screen? Ranjeev? So Pinaki, can you please share your screen? Pinaki, are you able to hear us? Go ahead, Pinaki. You're able to see your screen. We're not able to hear you. Roy, can you unmute if you're muted?
Yes. Can you hear me now?
Yes.
Okay. So hello everyone. I will talk on my project which I have pursued over 2 years at ISM Mohali. It is titled Thermonuclear X-ray Bursts from the low mass X-ray binary for U1636.
Hello, Pinaki, can you switch on your video also if possible, or are you having a bandwidth issue? At least for some, we can see you. Yeah.
Okay.
After some time, you can switch off maybe.
Okay. Can you see me?
Yes, we can see you. If you have a bandwidth problem, maybe you can switch off your video. Yeah, thanks.
Okay. So this is the outline of my talk. First, I will begin with introduction part, followed by my observation methods, and then I will proceed to the results and discussion. So a low mass X-ray binary, as you may have already heard from previous speakers, is a binary star system where one of the components is either a black hole or a neutron star. Yes.
Are you in full screen mode?
No, it's not in full screen mode. Yeah. Is it okay if I continue like this?
Yeah, continue, please.
Okay. So, and whereas the other component is a subsolar mass donor star, which fills its Roche lobe and transfers its mass to the compact star via Roche lobe overflow, as you can see in this illustration. So thermonuclear X-ray bursts or type 1 X-ray bursts are sudden eruptions in X-rays due to the unstable burning of hydrogen and helium on the surface of an accreting neutron star in a low mass X-ray binary. It is characterized by a sharp increase in the X-ray flux followed by a slow exponential decay. This is a typical illustration of a type 1 X-ray burst. Another phenomena is called a photospheric radius expansion or PRE burst. PRE bursts are a class of type 1 X-ray bursts during which the flux approaches the local Eddington limit, causing the photosphere to expand due to radiation pressure. And this is an illustration of a PRE burst where the three profiles, luminosity profile, temperature profile, and radius profile are shown, derived from spectral fitting. So a typical signature of PRE burst is that the at approximately constant flux near the peak of the burst, the temperature increases, whereas simultaneously the radius inferred from the spectrum decreases. So another aspect of type 1 X-ray burst is called short wait time X-ray burst or SWT bursts. Typically, X-ray bursts occur on time scale of hours or days. Can even within 45 minutes of the preceding burst. In that case, we call the latter burst an SWT burst or short wait time burst. Recurrence time as short as 3.3 minutes has been observed in a source, whereas for a typical low mass X-ray binaries, so far the shortest recurrence time is known to be 3.8 minutes. However, for this source, for U1636, the shortest recurrence time known so far is 5.4 minutes. And here is an example of a SWT burst taken from Berry et al. 2019, which shows a burst triplet. So the latter two bursts are short wait time X-ray bursts. So thermonuclear burst oscillations. So if we carry out the timing analysis of these X-ray bursts, we find some high frequency features in their Fourier power spectrum, typically in the range 300 to 600 Hertz, either during the decay phase or the rising phase or both phases of the X-ray burst. Here is a burst oscillation shown in the power spectrum of for U1636 at 581 Hertz. So they arise due to the modulation of brightness asymmetry occurring during the X-ray burst due to the rapid rotation of the neutron star. So our source for U1636 was discovered in 1974. It has an orbital period of 3.8 hours. The neutron star has a mass in the range of 1.6 to 2 solar mass, and the companion star is a main sequence star of subsolar mass. It exhibits a wide variety of X-ray thermonuclear X-ray bursts, as well as kilohertz oscillations and QPOs. It is a rare source which has shown all kinds of SWT bursts, that is doublets, triplets, and even a quadruplet burst. So moving on to the observations. So we have used data from two observatories. One is the NuSTAR or Nuclear Spectroscopic Telescope Array, which operates in the energy range 3 to 79 kiloelectron volt. It has a time resolution of 10 microseconds and a dead time of 2.5 milliseconds. We have found 15 bursts in one NuSTAR observation of total exposure 92 kiloseconds. We have also used data from our own AstroSat LAX-PC, which operates in 3 to 80 kiloelectron volt, and it has a similar time resolution. And however, it has a very low dead time of 43 microseconds, which makes it very suitable for timing analysis of such phenomena like X-ray bursts. We have found 26 X-ray bursts in 7 observations spanning 2 years of AstroSat. They have a total exposure of 270 kiloseconds. And here is the NuSTAR observation light curve showing the 15 bursts. You may see from the labels there are 2 doublets and 1 triplet. And this is the AstroSat light curve of one of the observations. 14 X-ray bursts. You may see 2 doublets in this observation. So these are the zoom in versions of those doublets and triplets. So there are 2 doublets in the NuSTAR observation shown in the first row, and 1 triplet in the NuSTAR observation shown in the middle. The doublets observed with AstroSat are shown in the second row. Typically, the NuSTAR observation, the short wait time X-ray burst have a wait time of 24 to 27, have a wait time of 8 to 11 minutes, whereas in the AstroSat observation, they have a wait time of 24 to 27 minutes. We have found for the first time the shortest recurrence time in one of the NuSTAR doublets, which is 3.8 minutes. This is the shortest recurrence time known for this source, for 1636. So I will move on to the results. So we have performed spectral analysis using the conventional method of burst spectroscopy, wherein we fit the burst spectra with an absorbed black body model known as T-BABS plus B-body in XSPECT. We have also performed spectroscopic analysis using the FA method, wherein it is assumed that the persistent emission may also evolve during the course of the X-ray burst. It was developed in 2013 by Warpel et al. And the PRE bursts, as we found from the signatures in their time evolution of the spectral parameters, that the PRE bursts have a peak temperature of around 2.7 keV, and the photospheric radius is found to expand up to 16 to 19 kilometers. The peak flux was found to be around 6.8 into 10 to the power minus 8 arc per centimeter square per second. We have found that the FA, which is a dimensionless parameter obtained from the FA method, lies in the range 13 to 17. We have also found for the non-PRE burst that the peak temperatures lies in the range 1.5 to 2.4 keV, and the FA parameter are in the range 5 to 10. So this is a typical non-PRE burst, wherein different profiles are shown. First one is the count rate of the light curve. Second is the temperature profile, then followed by the radius profile and the flux and the chi-square of the spectral fitting, followed by the FA parameter evolution. The green shaded region shows the region where burst oscillation have been found in this X-ray burst. Here is a non-PRE X-ray burst which we have found. Again, you may see the signatures of the non-PRE X-ray burst, where the temperature increases and the radius decreases while the flux approximately stays constant near the peak of the X-ray burst. Again, the green regions show the regions which show burst oscillations. So we have found burst oscillations in 5 of the 40 X-ray bursts we have studied. In 3 of the AstroSat observations and 2 of the NuSTAR observations. B2 and B10 are the NuSTAR observations, rest are the AstroSat observations. So the burst oscillation was found in the range 579 to 582 hertz, which is consistent with that reported in the literature. However, most of the oscillations are found in the narrow range of 580 to 581 hertz. One of the burst oscillation was found during the rise of the X-ray burst. So this is a dynamic power spectrum which Ranjeev sir was talking about, but this is drawn for burst oscillations. So here you may see the 580 hertz burst oscillation found in the non-PRE X-ray burst. So we have also studied the energy dependence of the amplitude of those burst oscillations. This we could do only for LAX PC because LAX PC had a good time, very low dead time, which enabled us to perform this sort of analysis. And however, this was not the case with the NuSTAR observation. So we see that the RMS amplitude of the burst oscillation increase with energy. The cause of this I will discuss later. So this is the phase folded pulse profile for the burst oscillation. This is shown for one of the instances where we have found burst oscillation. The fitting has been performed with the sinusoidal profile, and the y-axis is the intensity, whereas the x-axis is the phase of the oscillation. So from this pulse profile method, we have also tried to study the energy dependence of the phase of the burst oscillation, and we have found a soft lag in those in all the 3 burst oscillations. The cause I will discuss shortly.
Pinaki, you have only 2 minutes.
Okay, I am wrapping up. So moving on to the discussion, we have found for the first time the shortest recurrence time known for this source, which is 3.8 minutes. Only 3 sources so far have been known to show such a short recurrence time of 3 to 4 minutes. The short recurrence, the short wait time X-ray burst have been are showing on the rise times in the range of 3 to 8 seconds, and a long time scale of 11 to 20 seconds, which implies that the primary composition is hydrogen instead of helium, which may be true for bursts such as PRE bursts. There are two prevalent origin hypotheses for short wait time X-ray burst. One is proposed by Boyrin et al., which suggested that there is a waiting point in the chain of nuclear reactions, which halts the burst X-ray burst for a short time. However, their model could not explain the considerable spread in wait times. The second model was proposed by Keek and Hager in 2017, which proposed that some of the leftover fuel from an X-ray burst is carried to the ignition depth, and which results in X-ray burst a short time later. However, they could not explain the absence of intermediate bumps between two X-ray bursts, which their simulations showed. The burst oscillation during rising phase is commonly explained using the spreading hotspot model. However, during the decay phase, burst oscillations are usually explained using cooling wake and surface mode scenario. Cooling wake proposes that after an event of an X-ray burst, there is a cooling wake originating on the neutron star, which subsequently spreads, and the cooling wake scenario proposes that the amplitude should be typically over 10%, and whereas the surface mode oscillations proposes that the amplitude should be very low, as 5 to 10%. We have found that the FA parameter lies in range typically or especially near the peak of the X-ray burst, which suggests that there is a significant contribution of the persistent emission to the burst spectrum. The phase lag of the soft energy photons, which we have found, is usually explained by the modulation of soft hotspot emission by Doppler effect, which was proposed almost 20 years ago. And the oscillation amplitude dependence on the energy is usually explained that the low energy emissions from the cooler regions usually occur at they contribute to the background of the counts during the X-ray burst, whereas they significantly reduce at higher energies. So thank you.
Thank you, Pinaki. I don't think we have any time for questions. So thank you. Pinaki, can you unshare your screen, please?
Okay.
Any questions?
Yeah, thank you. Thank you.
So let's go on to the next speaker, Unnati. Can you share your screen? Unnati, we request you to please reduce your time if possible. Unnati, are you? Unnati,
I'm trying to share my screen. Yes, I'm there. I'm trying to share my screen. Hello.
Yeah. Hello, if there's any problem, we'll go to the next speaker and come back to you, Unnati. Shall we do that?
Yeah, please, if it is possible, please Could you do that? I will just join after that.
Ramadevi, are you there?
Yes, ma'am. So
Yeah.
I'll share my screen.
Yeah.
Yeah.
Go ahead. Also your video at least for a short time.
Yeah, sure. Okay. Are you able to see this screen?
Not yet your screen.
The screen is visible?
Not yet. Wait a minute. So all that is it you're talking.
Oh, okay. There's a firewall thing. Is the thing visible now, ma'am? 1 minute.
Going to standard mode, please.
Is that screen visible?
I will just see.
Is it visible?
Standard mode.
Actually, the previous screen is that needs to be unshared.
Yeah, so is that Unnati screen?
Yeah, I think.
Sorry.
I'm seeing the not Unnati's Pinaki's screen, I guess.
Hana picture screen is yours. Are you hearing us, Unnati?
No, I just left the meeting. I'm
Oh.
not sharing the screen.
Okay.
It says only one part.
Are
Can share it.
Are you sharing your screen? Have you unshared? Pinaki?
I have unshared my screen.
Yeah, okay. Rama?
Yeah, I'll do it again. I'll share it again. Is it visible? Ma'am, is it visible?
No.
Not yet.
No?
Can you go ahead and give your...
Try now. Try now.
Try now.
Yeah, I'll do it again. I'm doing the entire screen now. Is it visible? Is it visible? Is that visible?
No.
Huh?
So we're not able to see it, Rama. So go ahead and give your talk, Rama.
Okay.
Yeah.
But the PPT, it's not visible, huh?
Yeah, no, not even full screen. Even if it is not full screen, you can share. It's okay.
Yeah, but then, yeah, I'll give me a.
But sometimes full screen has a problem.
It must be from her side only because she's visible.
Yeah, that's one number. A hotline to him.
I'm surprised. Yeah, shall I leave and join again to see?
Yeah, meanwhile, we'll ask Unnati if she is able to come.
Okay, ma'am. Yeah.
Toggle between the two of you. Unnati, are you able to join? Because
Yeah, I am trying to share now.
yeah, because yours was the same source, So I thought we could finish your.
Yeah, okay, I'm trying that.
And even if it is not full screen, doesn't matter, Unnati.
Application from that. Yeah, okay.
No, you're connected to
Hello.
display.
Can you see my screen?
Okay.
Are you able to see my screen?
Not yet. We know we are connected to you. Your name is on the, but we're not able to see your screen.
Okay, I have shared it already.
Can you switch on your camera, please? Nothing.
Yeah, okay, I will do that.
Yeah, now we can see you.
But I have shared the screen already, so. Are you able to see my screen now?
Unnati, can I have your screen computer through any desk?
Sorry?
Can you provide me your desktop, remote desktop through any desk?
Any desk?
Yeah.
Okay, I can provide you my team viewer.
Just hold on. No, I don't have right now team viewer in my system. Do you have any desk at your?
Wait, I will try reshare. I will try to reshare my screen
Okay,
again.
so do one thing, stop sharing and just
Okay.
share the whole screen.
Okay.
There is an option downside on the left hand, share screen. So go with that. Sorry, on the top of the left hand, share screen. Can you find that?
Oh, wait, I am trying to. No,
Ranjeev, we don't have any issues at our end. So
wait.
So Unnati, you are using your laptop, right?
Yeah, I'm using my laptop. Can you see my screen now?
Now it's visible.
Okay. Wait.
Varun, can you confirm from the 104 that the screen is visible? Hello.
We are able to see the screen. Thank you.
Okay, should I start now?
Yes, please, Unnati. And can you make it a little fast? Yeah, fine.
Yeah, sorry. Yeah, hello everyone. I am Unnati Kashyap, a research scholar at the CIT Indore. Today I am presenting broadband time resolved spectral study of thermonuclear X-ray bursts from 4U6036-536 using AstroSat. So what are LFXVs? This has been mentioned in the earlier talks as well. These are the binary systems consisting of two stars revolving around a common center of mass. One of the stars is a neutron star or a black hole known as the primary component, and the companion star has a mass of around 1 solar mass. Depending on the source spectral properties, these systems exhibit different X-ray states. Two main states are soft and hard state. In the soft state, the emission is dominated by the seed photons from the accretion disk, that is formed around a compact object while accreting matter from the companion star. In the hard state, the emission is dominated by the high energy photons from a layer that is proposed to exist above the accretion disk, known as corona. So one of the most interesting observational features of neutron star LMXV is thermonuclear burst. The neutron star accretes matter from its companion star, and this matter gets accumulated on the surface of the neutron star. And this accumulated matter undergoes burning when favorable conditions are reached at the base of the accumulated column. And this results in a sudden increase in intensity of the system. The burning then propagates and spreads over the surface as shown. So why the studies of LMXVs and thermonuclear bursts important? Studying spectral and temporal evolution of these sources provides a better understanding of accretion physics and high energy X-ray emission mechanisms. Thermonuclear X-ray bursts are surface phenomena, and it helps to constrain mass and radius of the neutron star, and hence the equation of state. Additionally, study of thermonuclear flame spreading helps to understand the physics under extreme conditions, and thereby constraining the composition of the accreted matter. Peak flux of very bright PRE burst reaches the Eddington luminosity of the sources, hence it may be useful to measure the distances. So in general, the thermonuclear burst spectra are described by an evolving Planckian function with temperatures ranging from 1 to 3 keV. But in many recent observations, deviations from the Planckian spectrum is detected. Increasingly, such behavior is being observed with broadband and high sensitive observations. The possible reasons behind the deviation is proposed that this is maybe due to the reprocessing of the burst photons from the corona, or it can also be the reflection of the burst radiation in the accretion disk. It may also be the enhancement of the persistent emission due to the burst radiation drag on the inner part of the accretion disk. A precise burst spectral modeling is really necessary for applying bursts to put constraints on the neutron star parameters, as this physics behind this is still debated. So in this work, we searched the entire AstroSat database starting from 21 June 2017 to 20 August 2018 for bursts. The figure shows the hardness intensity diagram of the source, and it provides an overall idea of the evolution of the source during different observations. So we detected around 27 bursts with LEXPC and 15 bursts simultaneously with LEXPC and SX3. These are the observation details of the burst detected, and the figure shows the one of the bursts detected simultaneously with both the instruments. So we have studied and investigated the interpretation of the broadband spectra of this burst in this work. So why these studies are important? This kind of studies provides a better understanding of the burst and the accretion interactions, and the broadband capability of the AstroSat enables the detection of the excess in the spectra, as I have discussed before. Moreover, the good time resolution of the LEXPC provides a better scope to study the burst radiative behavior with time resolved spectroscopy of the burst. It also helps to understand the effect of accretion rate and spectral states on the burst. It manifests the requirement of the improvement on the existing burst models. So we carry out spectroscopy of each 4.7549 second during the burst. Here I have shown one such spectra. We fit the burst spectra with 4 models. The single blackbody model shown in black provides a pore fit, while the double blackbody model shown in blue, the parallel model shown in magenta, and the variable persistent emission model shown in red provides better fit to similar extent. And the shaded band here shows the 1 sigma error for the spectral fitting. This is more clearly shown here. Here I show the residuals obtained for each of the model, and except single black body, on all the double component model provides better fit to similar extent. And among the double component model, we couldn't clearly choose one over the other, but the double black body model is observed to provide less residuals more frequently among the double component model. Hence, we do the time resolved spectroscopy for all the bursts using single and double blackbody models. Here I have shown the results obtained from the time resolved spectroscopy of one of the bursts. For time resolved spectroscopy, what we do is we segment the burst light curve into small segment and we obtain the spectra from that and we fit it with different models. Here we choose single and double blackbody model only. And for comparing the models, we conduct F-test. That is, the second component will be considered only when the chance probability of the improvement of the fit is less than 27%. Thus, we put a threshold of 3 sigma significance on the chance probability through the F-test. Here I show the results of the time resolved spectroscopy obtained from one of the bursts. The first panel shows the temperature obtained from the single blackbody model and the cooler component of the double blackbody model in magenta. The second panel shows the temperature of the hotter component of the double blackbody model, and the third and fourth panel shows the Lexpc and SXT flux of both the models, and the fifth panel shows the normalization of the cooler component of the double blackbody model in magenta and that of the single blackbody model in blue. The fifth panel shows the reduced chi-square values of both the models. We also check the satisfaction of the threshold criterion using Protasov et al. Methodology, and no significant deviations was observed from the results that we have obtained from the F-test. That from our result, we have observed a significant excess near the burst peak. And for those intervals, F-test was satisfied, requiring the addition of a second component. This signifies that the interaction of the burst with the surrounding increases near the peak of the burst. Here I have shown the results obtained from the time resolved spectroscopy for a relatively fainter burst. For a relatively fainter burst, what we have observed that the F-test is satisfied for lesser number of beams, requiring the addition of a second component. Thus, the burst corona and burst accretion interaction increases when the flux is higher. These are the results obtained from the time resolved spectroscopy of all the bursts. So, the temperature of the cooler component of the double blackbody is observed to be similar to that of the single blackbody model, ranging from 1 to 2 keV, and the temperature of the hotter component of the double blackbody is observed to be greater than 2 keV. Moreover, the fit excess is observed for the beams near the peak of the burst, and addition of the second blackbody component is observed to take care of that excess. We also studied the evolution of the fluxes during the burst. So here I have shown the results obtained from the evolution of flux of the study of the flux of one of the bursts. The evolution of the total flux is shown in orange, and that of the flux of the additional component is shown in blue. It is observed that near the peak of the burst, the contribution of the additional component is comparatively higher than the other beams. So this signifies that with the increase in burst intensity, more photons interacts with the environment, indicating stronger burst accretion interactions. So now we know that the excess is required for several beams from the time resolved spectroscopy. So we try to understand its origin and how it is related to the burst properties. Figures show that the fraction of beams requiring the second component is mildly correlated with the peak flux of the burst and that of the duration of the burst. Thus, we can say that the burst accretion interaction is more for the burst with higher peak flux and long duration burst. We have also studied the variation of the flux of the second component with the total flux of the burst, considering all the beams used for the time resolved spectroscopy. And we found that both the fluxes are correlated. A Spearman correlation test performed between both the fluxes shows that they are positively correlated with a rank correlation coefficient 0.80. This implies two scenarios. Statistically, the higher signal to noise ratio for higher flux makes identification of the second component more prominent. Secondly, physically, the higher photon flux makes sure that there is enough photon particle interaction that deviates the burst spectrum from the Planckian model. Moreover, to compare both the fluxes, we performed a case test, and from the test it is observed that both the distributions are dissimilar, and from the distribution it is observed that at higher flux, for burst accretion interaction, higher flux is essential. So we have done a broadband study of So we have done a broadband study of all the bursts detected simultaneously with LXPC and SXT. We investigated the excess observed near the peaks of the burst. This kind of studies provides a scope to understand the deviation from the Planckian spectrum, which is not often identifiable with the instruments that are sensitive to soft X-rays. So this kind of studies manifest the requirement of the improvement of the existing burst model, including burst accretion interdictions. So thank you.
Thank you, Unnati. Are there any questions? Okay, there's a question from Ranjeev. Can you ask the question, Ranjeev? Ranjeev, are you there? Are you able to hear me?
You hear me?
Yeah, I can hear you.
Yeah, you can hear me, right? Okay. Okay.
Yeah.
So can you estimate a distance? I mean, not from the size of the two black body radius formed a normalization. See,
yeah, that we can do. If the distance, if we know the distances,
yeah,
then
so
yeah,
16 just, for typical 8 kiloparsecs, what kind of size do you get? Do you estimate? Have you estimated?
Okay, for this case, we have not done, but it can be done. I mean, it will give around. Yeah. Okay. What you're saying, I understood. I understand. Yeah, that can be done. Yeah.
So that'll give you an idea of the geometry of system of where the things are coming from.
Yeah. And for the as we are using two black body component, for the polar component, it gives around what we get in case of general neutron star system.
Yes, I know.
So our normalization is around. Yeah.
Okay.
Yeah. Our normalization is around 100. So from there we get. And for the given the sensitivity of the data, we couldn't constrain for the other normalization. I mean, for the hotter component.
Yes. Okay, thank you, Unnati. For the,
yeah.
Can you share the screen, please?
Yeah, sure.
Rama, can you come on? Hello, Rama. Yeah. Hey, Rama, can you?
You're muted.
Yes. No, she is speaking. Rama, you are muted.
Fine. Yeah. Okay. Can you hear me?
Yes, we can see you. Share the screen, please.
Okay. It says host disabled attendees screen sharing. When I try, the message comes disabled share.
It's at our end.
Yeah, can I?
Yeah, just hold on, Marama.
Yeah, sure.
Because it's cold, it's all automated here. So.
Okay.
Yeah. Yeah, now.
Yeah, yes.
So we request you to shorten the talk as much as possible, Rama.
Sure.
Sorry for this.
Yes.
It's also at our
Yeah,
end.
sure. It's
Have you shared your screen?
I am having issues. Please grant browser access to screen sharing. Screen recording. Wait, ma'am, there's some issue at my end, I think. Entire screen I'll share.
Yeah.
It's not coming up. Oops. Is it coming up?
Yeah. No, wait, we'll just see.
At the center of the screen, you can see the share screen green button. You can press that.
Yeah, I'm trying.
So
Yeah, I did.
on the top left, you will see the screen option. So you select that screen option and directly share.
Yes, yes. Yeah, that's what I'm doing, but it's not coming up.
All these people have done these things many, many times, but somehow there is an issue. So,
Ramaji, can you give me your system on remote? I can help you out.
Yeah, how do I do that?
now, can you share now, Rama?
No, it is. See, actually,
Do you have any desk on your system?
what do I have?
Any desk, remote software.
No, mine is a Mac thing.
Okay.
So, yeah.
Rama, we shared it with your LOC, the presentation.
Send it
No,
in.
I haven't. I can quickly email it. You can tell me.
No, Rama,
I
just
can
don't panic. Just go
quickly
and
do that.
tell us about your experiment.
Yes.
That's it doesn't matter if you don't show.
Okay. 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 Fine. Okay, ma'am. Okay, fine. Yeah, I can.
Don't worry.
Okay, fine. I'll just speak about that.
Yeah. Talk about it.
Yeah. Okay.
This is
Yeah,
a new
sure. Okay.
experience.
Yeah. Okay, fine. So basically, I am talking about the instrument, which is X-ray XPECT onboard XPoSat, which is basically X-ray, which is basically an X-ray payload. And XPoSat, as everybody knows, it's a polarimeter mission which is coming up. It's X-ray polarimetry satellite, and we have a polarimeter, hard X-ray, medium X-ray polarimeter, which works in the range 5 to 30 keV on board. And XPECT is an additional payload which works in the range 0.8 to 15 keV. And just a second. Yeah, 0.8 to 15 keV is the energy range for XPECT, and it largely does the spectroscopy and timing studies of X-ray, select X-ray sources, like black hole binary systems, neutron star systems, AGNs, accretion-powered pulsars, cataclysmic variables, etc. So there are a list of sources which are chosen, bright X-ray sources that are chosen to do both polarimetry study as well as spectroscopy and timing studies. So if I were to tell the science objectives of XPECT, as I mentioned, it is to do spectroscopy and timing. But what is unique about XPECT is that although we have many number of spectroscopy and timing instruments already on board, which is observing these sources, the uniqueness of XPECT is that we will have a option to continuously monitor these X-ray sources which are pointed towards. So the polarimetry instrument on board XPoSat will have to look at these select X-ray sources for a very long duration of the time, like for weeks to months together. And so we take the advantage of that because XPECT will also be co-aligned with the polarimeter on board XPoSat, and it will observe the sources for weeks to months together in a continuous day-to-day basis. So that is the primary advantage of XPECT. So XPECT instrument as such, it is a semiconductor-based device detector, which is a swept charge device, which is similar to, as you would have known, silicon devices. This is a silicon-based device, swept charge device, and a soft X-ray spectrometer. So we will have an geometric area of about 64 centimeters square. Two modules are placed on board, and each module, out of the two, one will have a 2x2 square degree field of view, and the other will be 3x3 square degree field of view. And the effective area, if you consider, that will be about 30 centimeters square to observe these sources. So an energy resolution to be highlighted is that it will have 200 EV at 6 keV. So we have a good energy resolution to do line profile studies also. And the operating temperature is -20 to -40 degree, which is generally a semiconductor detector operating range. So as I mentioned, doing a spectroscopy in the soft X-ray 0.8 to 15 keV, we to be highlighted is that 0.8 keV is also included, sub keV, less than 1 keV, as compared to the present missions which is on board. None of them work below 1 keV. So the broad science goals to highlight are like the origin of soft X's. When you go lower than 1 keV, we take the advantage of having good enough efficiency at lower energies, and at the same time observing bright sources with a swept charge device. We do not have pileup effects, so we gain the capability of doing spectroscopy at energies less than 1 keV, and to continuously monitor these sources. And so study of origin of soft X's in these black hole sources, as well as the cataclysmic variables, which have been done by Susaku and other missions, wherein there are some sources where soft X is observed, but still the modeling of the spectra is not sufficiently done. So by using XSPECT, continuously monitoring these sources, we'll be able to speak about the natural variability and the origin of soft X's in these X-ray sources. The second objective is evolution of X-ray spectrum of these neutron star and black hole binary systems. Basically, the spectral state transitions. As you would have known that till date, all these X-ray sources which have been observed, we have been doing like a one-day cadence observations. When an outburst is observed, it's a few kilosecond of observations scheduled to observe these sources. And so in a day, few kiloseconds is observed, and then because the time constraints exist to get the allocation of time from these major missions. So we will have just few kiloseconds of observation in a day, and then move on to other sources. And so every day it's just one data point which exists, and we do the spectral evolution of these X-ray binaries and any X-ray source till date. But with XSPECT, we will continuously monitor these sources. And so the time cadence will be like few hours time scale. So the spectral state transition happening in these X-ray sources can be studied to a cadence level of few hours. The next objective is like study of FE line profile and the flux variations. So we all know that FE line have been explicitly seen in X-ray binaries, both black hole systems, neutron star, as well as AGNs. But then again, limited study of these ion line profile and the variability of the line profile along with the intensity on a continuous basis has not been done in these sources, and which XSPECT will be able to do with its very high spectral resolution capability. And continuing the study of evolution of spectral state transition and line profile, we will be able to do this mass and spin measurements of the black hole with huge amount of data by continuous observations. Then as there are other sources like magnetars and accretion powered neutron star systems and AGNs, which has also been observed. So in these neutron star systems, the spin period evolution along with changes in X-ray flux emission mechanism will be studied, and in AGN also temporal variabilities in the soft X-ray band by continuous monitoring will be carried out. So above all these, one niche science which will be attempted with this XPoSat is that because we have the polarimeter as well as the spectral and timing temporal instrument and studying instrument XSPECT on board, we will be able to do spectroscopy, timing, and polarimetry of these select X-ray sources simultaneously, which is the first of its kind. Till date, we have not done such a study in this X-ray astronomy. So that's a niche thing which we'll be attempting on. So, and I don't have to introduce the group to X-ray binaries. All of the participants will be familiar because we have been going into the details of the studies by the previous speakers. So basically, binary systems are the compact object with the companion, and all of us know that spectral state transition happens from as the instrument, as the system goes in an outburst, you have a rising phase which goes to the high soft state, and then you have the intermediate, and then getting back to the hard state. So these spectral state transitions, which have been studied with very less cadence, will be studied in detail by XSPECT thing. So it will be the first ever observation of a single source for very long durations from, and we will be, if source is in an outburst, we will be able to cover it from the start of the outburst till the end without even a break in between, and which breaks come because of the operational constraints in the orbit due to SAA passage, etc. But otherwise, we will have a continuous observation. So the Q diagram and the hardness intensity diagram, whatever studied till date, the data gaps which we have in them, we will be able to cover it up and hope to get some new information from that. Also, persistent sources where like Cygnus X1, the best possible time cadence discussed till date for Cygnus X1 is like 3 hours or so. With this, we will be able to attempt to do it better for the spectral studies. So from the timing point of view, we have a temporal resolution of about a millisecond. But for these bright sources, co-adding many observations together, we will attempt to do the pulse profile study as well as the QPO study as much as possible, because we have limited area. Vouching on doing a QPO study will be very too optimistic. So, but definitely finer temporal variations in the light curve with the lead lag studies of hard, meaning different ends observation, will gain some information in that. Then, yeah, so long-term monitoring is one of the niche thing which comes out of this XSPECT observations.
Yeah.
And temporal variability. Yes, ma'am. Yeah. So yeah, temporal variability, we go from millisecond time scale, like for example, crab is a 33 millisecond pulsar. So by observing it, we have simulated, the plots are there in the PPT, but unfortunately I'm not able to show that. So simulations indicate that about 2 kilosecond observations of these, of crab like bright source with the 33 millisecond period, we will be able to pick out the pulsations. So there are list of pulsars which are planned in the XPoSat observations, and in the first year observations itself, continuous observation of these pulsars, we will be able to study the pulse profile variations over time. Because when you co-add the light curve, fold the light curve, you will be able to get the pulse profile variations. And also like fast variability exhibited in GRS like sources, we'll be able to do seconds to minutes time scale study in such persistent sources. And of course, like I said in the previous points, like during the complete outburst, which goes from weeks to months, that will also be able to that will also be studied with XSPECT. So there are a few simulations which have been shown in the PPT, showing that 10 kilosecond observations of bright sources like Cygnus X1, a black hole system, and the GX17+1 with just exposure time 10 kiloseconds, we will be able to decouple the components in the spectra, like the multicolor disk black body, the Paolo and the Gaussian line, the FE line. And so with a 10 kilosecond cadence, we will be able to tell the evolution of the spectra and various parameters. Then in accretion powered pulsars, you will have, by folding the light curves, we will have different pulse profiles. Yes, ma'am?
1 minute.
Yeah, yeah, okay, fine. So, okay, fine. So all the few of the plots here, I have the simulations shown, which clearly indicates that within a few kiloseconds observations, all these sources can be studied in detail, and the spectral parameters can be studied carefully. And yeah, nature of the soft component, simulations of Cygnus X2 for just with 5 kiloseconds, we are able to fit the data with multicolor temperature, or that the soft axis can be explained with just the 5 kilosecond observations. Then one another important information is that the pileup free observations of bright sources in soft band, all of you would have known that XMM, Chandra and Swift carry out observations of these bright sources, but however, when in the soft state, these are pileup issues are there, and so there are limitations to model the spectra in detail because of the errors which come up due to the pileup. So largely, most of the observations are not handled in the event mode due to pileup issues, but XSPECT can handle that, and that we take advantage of this high counted capability as compared to the existing missions. Even with a smaller effective area, we will be able to do good spectroscopy and timing. So yeah, I finished with the last point that the niche science objectives which will be covered with this XSPECT is that simultaneous spectral, temporal, and polarimetry observation of select X-ray sources for the first time will be carried out. That is the primary niche science. The second point is continued long-term spectrotemporal observations, which will give a higher time cadence of about few hours to study the spectral state transitions, and also the FE line profile and flux evolution of these bright sources in few hours time scale can be carried out. So these are the three primary science, niche new science, which can be brought out from observations of select X resources with XSPECT. Thank you.
Thank you, Rama. You can share
Yes, ma'am.
slides on the Slack channel. The Slack is enabled.
Yeah.
So you could
Okay.
share it later. Yeah. Thank you. I don't think there are any questions online. So in case there are questions on Slack later, you can answer.
Okay.
Thanks a lot, Rama. Sorry for to both you and Unnati for this problem in our sharing the screen. Thank you.
Thank you, ma'am. Thank you.